Hey everyone. In today's lesson, we're going to be looking at interest. So this lesson will be largely focused on money and ways that we can earn money on our money. We are going to look at simple interest, compound interest, and then a type of compound interest called continuous interest. Okay. We'll start with simple interest, which is where you earn interest only on the amount of money that you start with. Okay, so you make an investment, you earn money on it, and it only earns on that initial investment. There's two different ways that we can write out a formula for this. The first is in terms of the amount of interest that you make. So I is equal to P, not R, PRT. Okay, where principal is, that's a word that we're going to use a ton today, so make sure you know what that means. Principal is the amount of money that you start with, the amount of money that you invest. R is going to be our interest rate, and T is going to be time. So multiplying those three together will give us the amount of interest that's earned. If instead we wanted to see the total amount of money that you end up with, including the principal that you start with at the beginning, we would use this second formula. A being our total amount is going to be equal to the principal times 1 plus the rate times the time. Okay? Depending on the context, you'll use one versus the other of those. Simple interest is going to be a linear function because it's just earning interest on that beginning amount, so it's going to increase by a set amount each year. Okay? On the other hand, compound interest, which is what we'll be spending most of our time with today, is where you make an investment and you earn interest on that investment, and then once you earn interest, you continue to earn interest on that new amount. So it grows at an increasing rate. Okay? Compounding interest is an exponential function instead, and we know that exponential functions will grow faster over time than linear functions. Okay? The formula for this looks pretty complicated, but you'll get pretty used to it as you just start to use it more and more often. The formula for this is that the amount that you end up with after a certain amount of time is equal to the principal that you invest times 1 plus the annual rate of interest, or whatever your time frame is, divided by the number of times that it compounds, meaning it might compound and give you a new amount every month. And in that case, your n value would be 12, okay? Or maybe it does it every day, and in that case, your n value would be 365. And then it's raised to the n times t power, okay? You'll get used to using it as we go throughout it, but just come back and reference it as needed when you need to use that formula. We're gonna look at two examples here to kind of compare the two ways of earning interest, okay? In example 1, we have a savings account that starts with $4,500, and he has the chance to earn 4.7% interest, but just a simple interest for 5 years. How much money will he have at the end of that time? And then in example 2, we'll look at it instead with a lower interest rate, but with a higher growth because it will be compounding monthly. Okay, well, a higher growth in comparison. So to start with, we want to calculate how much money he'll have at the end of 5 years for the simple interest loan in example 1. We'll say A, our total amount, is going to be equal to the principal, so $4,500 invested, times 1 plus the interest rate, which as a decimal will be 0.047, times 5, the amount of time that we have for this. And if we plug that into our calculator, we're going to get out about $5,557.50. Okay, so earns a good amount of interest in those 5 years, over $1,000. Okay, in example 2, let's go ahead and look at it with the monthly compounding instead. We can see in this one that the interest rate is lower, so I would expect it'll be harder for it to grow. But since it compounds monthly, that will help it at least grow at least somewhat better. Okay, so for this, we're going to have our principal multiplied by 1 plus the interest rate, which will be 0.042 from the 4.2%, divided by, in this case, we're compounding monthly, so n is going to be 12 times that it'll compound per year, raised to the n, again, 12 times t. Okay, so raised to the 60th power. Again, we'll take that, we'll put that into our calculator, and when we get that out, it's going to come out as $5,549.52. So it ends up being a little bit less than the simple interest account, but the interest rate, though it may feel pretty close, is actually fairly significantly lower. That 0.5% makes a big difference. And the compounding helped it grow and kind of catch up over time. Okay, let's go to the next page, and we're going to take a look at a few examples here, but not too much. We'll skip past most of it for now. Let's take a look at example 1, just to see a problem where we'll calculate the actual amount of interest that's earned on a simple interest loan. Okay, in this one, there's a $70 loan, and 5% simple interest is charged for this 1 month. Okay, how much interest will need to be paid? So in this case, I'm going to use the simple interest to not get the total amount, but the interest amount. So I'm going to say equals PRT, okay? And so here we're going to say interest is equal to the principal is $70 times the rate of 0.05 times the amount of times that it will have to pay out that interest, which is just once for the month. Multiplying those out, we'll find that it would be $3.50 of interest that needs to be paid in addition to the $70. You can see a few other examples below that will practice with these types of interest. You can pause the video and work on those if you want, but I'm going to keep going down to number 4 right now. Okay, and on number 4, we've got a couple types of compounding shown. Okay, so it's got 2 people are investing in $400 into an account at 3% interest. But the difference between these is the frequency of the compounding. So in the first case, it compounds monthly. In the second case, it compounds annually. So let's see how that makes a difference, okay? First, we'll write out the formula for each of them. So we're going to use our compound interest formula here. So I'm going to say A is equal to 400, our principal amount, times 1 plus the interest rate over compounding monthly for Dylan, so that's going to be 12 raised to the 12 times t. We're just doing this as a general formula right now, not over a specific time frame. And then for Nolan, it's going to look very similar, except this is only compounding annually. Okay, so our n value is going to change from 12 to 1. It's going to be raised to the 1 times t. And if we wanted to calculate this for 10 years, we would do that below. Go ahead and pause the video, and I want you to do a calculation for that to figure out how much each of them would have after 10 years. When you do that calculation, you should find that Dylan will end up with $539.74, and Nolan will have $537.57. So we see that at the same interest rate, one account grows faster because it compounds more frequently. So Dylan makes more money in that time, not a ton more, but in this case somewhat more, by compounding more frequently. If we look at number 5, we've got the same situation, except this one's compounded daily, okay? And so if we give this one a try, and I write out a formula for this, so we've got the same $400 is invested, and it's still at a 3% interest rate. This time it's compounded daily, so 365 times in 1 year. And if we want to see how much that makes in a year, or in 10 years, to compare to Dylan and Nolan, we can plug in 10 for T. And so go ahead and pause the video, calculate that, and you can write your answer there for number 6. And in this case, we're going to find that it would be about $539.94. Okay. What we can see happening here is that the least frequent compounding yielded the least amount of money. Then more frequent compounding yielded more money, and the most frequent compounding yielded the most money. Now, these are not super different numbers, right? If you ended up with $2 less after 10 years, I don't think it's going to make a big deal to you. But in situations where the interest rate is higher, those differences can really add up, okay? So the main takeaway from this is, in comparing these, that more frequent compounding increases the interest that's earned. Now, you may be thinking, can we just compound more and more frequently and therefore earn more and more money? Okay. And we're going to try this out and experiment with this on this next page. Okay. So going to the next page, we have a hypothetical scenario where we decide to invest $1 at the start of the year, and that we earn 100% interest on it in that year, which would be awesome if we could do that. And we're going to be able to compound this in times per year. We are going to try to see with that frequency of compounding, or with a higher frequency of compounding, are we able to earn more and more money? Are we able to earn infinite money if we just compound more and more frequently? Okay. So for this scenario, we're starting with $1. So $1 is our principal times 1 plus our interest rate is 100%. So as a decimal, that's just going to be 1 over n raised to we're doing this for 1 year. So 1 times n power. Okay. And we want to figure out, under these different scenarios, under these different frequencies of compounding, how much money will we earn, okay? So for example, if we compound yearly, okay, that's just gonna compound once per year. So if I wrote out my formula, and you don't need to fully write out the formula every time, it'll get very tedious as we go through all of these. So don't feel compelled to write it out every time. Just gonna have a bunch of ones in that case. And if you just simplify this, you'll see that you will end up with $2 at the end of the year, which makes sense. We're earning 100% interest, and we only compound at the end of the year. So we just get that 100% interest at the end, and we've doubled our money. Let's say that we wanted to do this semi-annually. So that means twice per year. Okay. So our starting amount, this time it's just our n that's going to be changing. And if we run the calculation for that, it's going to end up as $2.25. So actually a pretty significant improvement in that case. 25 cents, which on a total amount of $2 is a pretty significant portion. Okay. I want you to pause the video and go through and fill in the rest of this table and see what you notice as you go through that. Okay. So try it for the rest of these and see what you come up with and see if you notice anything about these values. Okay, I'm gonna scroll down to my filled-in table so I don't have to rewrite all of that in this case. And what we can see as we compound more and more frequently, each time that we compound, we make more money, right? It's better for me to compound twice than just once, right? It's better to compound weekly than quarterly. It's better to compound daily than weekly, and so on, right? The more that we compound, the better, right? Because it gives the money another chance to start earning interest on a larger amount. What you probably also noticed is that as this value increases, it's getting diminishing returns. So though it's going up, it's starting to flatten out. It's kind of like an asymptote that it's approaching a certain value, okay? And once we get up to the point of compounding daily, we're hardly seeing any change up through 1 billion compounds in a year, right? We're still at about $2.71 roughly for any of those outcomes. And what it's ultimately doing, as n gets larger and larger, say you wanted to try it 1 trillion times or more and keep going with larger and larger numbers, it will increase ever so slightly, but we reach that point of diminishing returns, okay? And this approaches a value of, this will approach a value of about 2.718 or so, okay? This number is called Euler's number. It is represented by the letter E. This came up really briefly in our last lesson. We saw it show up once, okay? And so E represents that value. You can find this on your calculator. If you, let me see if I can find it on here. If I go to my calculator, right here, that will give me E. So if I did second divide E, if I hit enter on that value, we see it comes out to about 2.72, okay? So this is a really important number in math, and it shows what happens when we compound continuously, okay? And so like, would this number ever hit $2.90 at the end of the year? No, we're gonna be maxed out at about $2.72 on this with continuous compounding, okay? So if we compound constantly with no breaks at any point ever. And if we think about this with our compound interest formula that we see written down here, well, if we approach infinity with that n value, if we plug in larger and larger values, so we get a larger denominator, but we also raise it to a power more and more times, this formula actually simplifies itself down into something that's easier to work with, okay? And it becomes this. A is equal to the principal times E, Euler's number, so 2.72 roughly, raised to the RT power, okay? We call this PERT as a shortening for it, okay? And anytime we're dealing with compound interest, we can just use the PERT formula rather than, anytime we deal with continuous compound interest, we can use this rather than the more complex compound interest formula, okay? Let's go down, let's talk about it a little bit more here. Okay, so if we wrote it again, our total amount at the end is going to be equal to P times E to the RT power. We know that R is our interest rate in this case, okay? And one thing that I'll say is that we can see continuous compounding come up in a few cases. Everything that we've talked about so far in these notes have been pertaining to money. This can also come up when we're looking at how a population grows over time. It can grow in a continuous way. Or you may have seen in chemistry when radioactive decay occurs, okay? And in radioactive decay, of course, the value is decreasing. And how would we deal with this? How would we deal with this formula if it's decreasing? And what we'll do here to account for that, if there's decay, is that the R value would become negative. Okay, so say it was decaying continuously at a rate of 2%, then our R value would be negative 0.02 in that case. Continuous interest is the only time where we will use a negative R value if it's decaying. No other time do we use this, but for continuous interest, we'll see this happen if it decays. All right. Let's keep going. I'm just going to pick out a few more examples for us to see and to practice with. Okay, let's say we'll go down to number 3. And on this one, we're going to look at a situation where we're earning 8.2% annual interest and we are compounding continuously. Okay, so we're going to apply PERT in this case. And here, Reagan is investing $1,000. We want to see how much will there be in 1 year, 10 years, and how long will it take to double the money. Okay, so let's take a look through all of these. Starting with part A, how much will there be in 1 year? So I'm just going to use my PERT formula. And like I said, this is simpler than the compound interest one. So it'll be 1,000, our principal, times E to the R, so 0.082 times T, which is 1 in this case. If I run that on my calculator, I'm going to get that about $85 will be earned on this at the end of the year. Then on B, in 10 years, so I'm going to do the same thing. My exponent is just changing. I'm now using 10 instead of 1. Okay, how much would we have? 10 years would yield $2,270.50. Okay, so you can see the impact of leaving money invested over a long time. You're really able to earn a lot on that. And then for C, okay, how long will it take for the money to double? Well, we see that by 10 years, it had already done more than doubling. So I expect it'll be a little bit less than that. Let's go ahead and try this. So if it's going to double from starting at 1,000, that means we would end up with 2,000, right? So 2,000 is going to be equal to 1,000 times E to the 0.082. We're trying to figure out the time, so T is going to be our variable in this case, okay? And as we've done before, in order to solve this, we've got our variable up in the exponent. And when that happens, we'll eventually learn to solve that with a logarithm, but for this unit, we'll be solving it graphically. Okay, so I can go over and graph this. First, I'm going to simplify this down, and I'm going to do 2,000 divided by 1,000, and say 2 equals E to the 0.082 times T. And I'll take this, and I'm going to go ahead and graph this. Okay, so I'll graph the left side and the right side. So I'm going to say y equals 2, and y equals E to the 0.082 x power, I'll say. And I'm going to look for where these lines overlap. And it will double after 8.45 years. So time to double would be about 8.45 years, which is pretty good for putting money in an account and never touching it, right? That you get double your money in less than a decade. Okay? Now, everything that follows this is just more practice with these same ideas. So I'm not going to continue to go through it in the notes. I'll have you guys work on this and practice it from here. But the main takeaways from today are looking at how we would calculate simple interest, how we would calculate compound interest, which, like I said, we deal with quite a bit more. And then lastly, dealing with continuous interest in our newer formula of PERT, okay? So I'm going to end the video there, and I'll have you guys practice more in the notes from here.